interpreting here. All right. Okay, so let's take a look at the scenario here that we're looking at, in terms of this particular memoranda. So the molecular pharmacology lab is trying to determine what type of receptor our compound interacts with. While we don't have any receptor binding data yet from the lab, we do have other information that may provide us with some clues about how this drug might work. They have exposed cardiac muscle and vascular smooth muscle cells to our compound and have begun screening for second messenger activity. So we're going to be taking a look at a little bit of second messenger stuff, nothing that's too not a whole lot more than what you learned in biochemistry, but you should know enough to be able to kind of muddle your way through this. Please note that our marketing team did not like the name JC001 and has renamed the compound Unknownalol. Based on the data below, what reasonable conclusions can you make about the general type of receptor that Unknownalol interacts with? Okay, GPCR, ligand-gated ion channel, enzymatic, nuclear, or cytokine. The types of signal transduction mechanisms affected by Unknownalol. And these are the second messengers, remember from biochemistry. Second messenger systems are those biochemical reactions that occur inside of a cell when a receptor is activated. And the real role of second messenger systems, as we're going to learn in a couple of weeks, is to transmit the information that's carried by the ligand molecule into the cell so that it can change the cell's function and activity. Okay. What cell type seems to be most sensitive to Unknownalol, and the specific types of receptors or receptor families that may be targeted by Unknownalol? Okay, so we're making guesses here. We don't know for sure, but we're kind of extrapolating based upon some information. So let's go down and take a look at some of the data here. Okay.
Dr. Cohen.
Yeah.
Was there somewhere to upload this on?
No, you know, Priscilla, not yet. It will be, I would say, as long as you guys have it, done. I'm going to work on getting that done tonight or tomorrow. I won't be due till the end of the week. Okay. I wanted to go over it today. I wanted you to have it done for today, but I will set the assignment until Friday for you guys to upload. Okay. And there will be two separate assignment uploads, one for Memoranda 2 and one for Memoranda 3. Okay. And like I said before, I'm not grading these. You'll get credit for it as long as you made the attempt to do it. Okay. And, you know, if you need to make some corrections today or whatever, that's fine too. Okay. All right. Oh, and one other thing too that I wanted to tell you. So just another quick piece of housekeeping item that I forgot. Today and tomorrow, I'm actually not even supposed to be in the office, but because of COVID, I'm supposed to be in DC. I'm on the American Associations of Colleges of Pharmacy annual program meeting or annual meeting program committee. And so it's an all-day meeting. So and it starts at 10. So what I'm going to do today, if you guys don't mind, is we're just going to work all the way through to 10. If you need to take a restroom break or walk away from the camera, okay, that's not a problem. Okay. That's totally cool. But what I just need to be able to do is to leave at 10 o'clock today. Okay, so you have a little bit of time at the end. If you're trying to get a hold of me, okay, today, like I said, I'm going to be tied up, okay? I'm going to be tied up most of the day until 5 o'clock, and then I'm teaching history of pharmacy at 5:30. So the next 2 days are going to be pretty busy. I'll try to get back to you if you need anything, but I appreciate your patience as I kind of work through this, all right? Okay, so let's take a look at the data here. Okay, so if you guys aren't, let me see if I can make this a little bit easier for everybody to see here. Okay, so what a lot of this really involves in terms of answering Memoranda 1 is interpreting graphs. Now, if you're like me, okay, you know, interpreting graphs can be a little bit of a tricky thing, and it takes a little bit of time to kind of be able to navigate what their meaning is and to see where things are located and understand what's going on. So when I start this off every year, what I try to give students is a basic framework for analyzing graphs. Okay, you know, one of the first things that I think is important is to really take a look at, when you take a look at a graph here, and it's going to be a little bit tiny, but take a look at the title of the graph. The title of the graph will tell you an awful lot about what it's trying to illustrate. And in this one, it's the effects of unknownalol on membrane potential. Okay. The next thing I do is I will go either over to the key, if there is one, and there is one here. Okay, we have two different types of bars here. One that represents resting membrane potential, okay, and another one that represents the effects on membrane potential when 10 milligrams of unknownalol is added to our cells, okay? Now, let's go down here on the x-axis. We have three different muscle types, or three different cell types. We have cardiac muscle, we have an SA nodal cell, and we have smooth muscle cells. Okay, and then we have the corresponding bars that go along with those. Okay, and then we have membrane potential on the y-axis. Okay, so let's take a look at this particular graph here. So if we take a look at the resting membrane potential for cardiac muscle, about minus 90 millivolts. Okay, when we add unknownalol to that, okay, is there any change in resting membrane potential?
No.
No, there isn't. And I'm talking about, and again, if I give you a graph on an exam and I want you to see that there's a difference between two data points or two bars, it's going to be huge. Okay. If it's really close, you can assume it's the same. All right. Over here, SA nodal cells, what about that? Is there any effect on unknownalol on SA nodal cells membrane potential?
No.
Nope. Okay, they're all the same. So, you know, resting is about minus, I'll say about minus 60. And when we add unknownalol, it doesn't change. So there's really no impact there. And then the resting membrane potential for smooth muscle cells. Any effect of unknownalol there?
No.
No. Okay, so what receptor type do you think we could perhaps eliminate here?
Is it the G protein complex?
Not Eric. I think it could be depending on if the receptor is coupled to it. But I was looking for an even more just even a simple. You got a kind of a more complicated answer there, but I was looking for even a little bit more simple answer. What type of receptor, when it's activated, changes membrane potential?
The ligand-gated ion channel?
Yeah, the ligand-gated ion channel. So that's really what I was going here. It is certainly true that GPCRs will activate a ligand-gated ion channels and change membrane potentials, and we'll learn about that later on. But really what I'm doing here is I'm just looking at, if you apply this drug to the cells, is there any change in membrane potential at all? Does it activate those ligand-gated ion channels or inhibit them? Okay. Is there any change there? No. Okay. So we can eliminate ligand-gated ion channels as a possible cell receptor type that this drug interacts with. Okay. Let's go down to the next graph. IP3 data. Okay, now we haven't talked about this specifically, but you guys have learned about the inositol trisphosphate pathway in Dr. Skabinski's lecture. The only thing that you need to know right now, even to answer this question, is that IP3 is a second messenger. That's all you need to know. All right, that's activated by what types of receptors? Do you guys remember what types of receptors activate IP3?
GPCR.
GPCR. So Eric, this is where your GPCRs come in right here. Okay. All right. So we've got our title here. Okay, of our graph. Okay, and then we go over here to our key. The black bar is basal levels of IP3. That means IP3 that's produced when the cell is at rest. Okay. Norepinephrine. When we add 10, just move this window out of the way. 10 micromolar of norepinephrine. That's the red bar, and then 10 micromolar of norepinephrine we add to the cells plus unknownalol. Okay, so let's take a look at cardiac muscle here. Okay, cardiac muscle, our basal levels of IP3 are about 3 picomoles per milligram per tissue. And again, don't worry about that so much. It's just the number 3 is what's really important there. Okay, what happens when we add norepinephrine to those cardiac muscle cells? What happens to IP3 levels?
Increase.
Yeah, they increase, right? Pretty significantly. We go from about 3 to 7. So there's a significant increase there. Now, here's the key. When we add norepinephrine again, This time we're going to add a inonolol with it. And what happens here to IP3 levels? See that there?
They drop.
They drop back
compared to
down.
this norepinephrine.
Yeah, almost back down to basal, right? So what do you guys think is going on here? What is inonolol doing?
It's probably blocking those receptors.
Yeah, it's probably blocking the receptors that are responsible for activation of the IP3 pathway. Really good. That's great. Everybody got that? Any questions about that?
Yes, I have a quick question.
Yeah, Tasheen, go ahead.
The an antagonist then, because it blocks it.
It could be. So again, that's a reasonable hypothesis right now. Okay, it's a reasonable hypothesis. It looks like that was what it could be. Okay, let's continue. SA nodal cells. Here's basal levels of IP3 right here. Norepinephrine doesn't change it really at all. And when we add norepinephrine and inonolol, we don't really get so much of a decrease there, do we? Okay, these are all pretty much the same. You know, they're error bars. This might be a little bit lower, but I would argue here that inonolol doesn't really have any impact on SA nodal cells. Certainly not like it does in cardiac muscle cells, right? And IP3 levels. Let's go over to smooth muscle cells. Okay, smooth muscle. So when basal levels of IP3 are about 4 picomoles per milligram of tissue. Okay, when we add norepinephrine to it, look how IP3 levels go up. They go up to almost 9, right? So there's a big increase. And IP3 is an important second messenger system in smooth muscle. Okay, and then when we add norepinephrine again, along with inonolol, look what happens to IP3 levels. They fall again, right? So what can we say here is, does inonolol have any effect on smooth muscle cells? What do you guys think?
Yes.
Yep, absolutely they do. Okay, so we've got 2 cell types here. And what type of receptor do we think inonolol is probably interacting with? What class or family of receptors? Type of receptor? What's that?
Adrenergic?
Well, that could be, right? Absolutely. Let's go up another 10,000 feet. So it could definitely be adrenergic. I think that's where we're headed here. But what type of receptor? What type of receptor is an adrenergic receptor?
Would it be GP?
GPRs.
Yeah, GPCRs, right? So that's what we're getting at here. So you see, we're kind of using deductive reasoning here to figure this out. Okay?
I have a question, Professor.
Yes, Roberto, go ahead.
The inonolol are working as a competitive ligand with.
So yeah, go ahead, Roberto. So competitive,
Like,
is it like
Is competitive with norepinephrine.
Yep. So again, we haven't gotten that far yet in the notes, but it sounds like you guys have a little bit of knowledge of antagonists, which is really good. So the type of antagonist, so what Roberto's hypothesizing about is the type of antagonist as this might be. We know it blocks the receptor, and he's hypothesizing that this might block the receptor in a competitive manner. We haven't talked about that yet, but we will today. Okay, I'm pretty sure we will get to that today. And so let's move on. Okay, but that's a good thought, Roberto. Let's keep that in mind. Okay.
Dr. Cohen,
Yeah.
I have a question about this graph.
Sure.
So, looking at it, like I would have thought if you look at the basal levels
Yep.
compared to even like the norepinephrine and inonolol, because I know you said that SA node, it doesn't have a big effect.
Yeah.
But I thought it did because like it's even lower than the basal level.
Yeah. You know, and that's, you know what, if this were an exam question and you were to tell me that there was a reduction there, I would give you full credit for it. Okay. Because, you know, we're not, you know, again, we're not splitting hairs. I don't like to do that, especially on exams. I mean, we can discuss this in, you know, in this kind of environment and, you know, because it's a kind of a safe environment to make a bad decision or a good decision in terms of what the answer is. But I would not debate that with you. I'd give you full credit for that. Okay. What my intent here was to say, to let you know that as compared to the cardiac muscle cells and the smooth muscle cells, there's really not that much of a robust effect on IP3 and SA nodal cells. Okay. But I can see what you're saying there. All right.
Dr. Culhane, I have
Yeah.
a question on this one too. So I know you said it doesn't have much effect on the SA nodal cells.
Yep.
But would a nodal wall still be blocking receptors for IP3 with like norepinephrine and a nodal wall together, or no, because or not as significantly?
Yeah, not as significantly, Kayla. I mean, I think that, what we're beginning to get the picture of here is that a nonalol, okay, will block a GPCR that when activated leads to IP3 generation, right? And so, and we can see that in at least two cell types, okay, a nonalol blocks that receptor really, really well and has a significant impact on IP3. If you look at SA nodal cells, okay, IP3 generation doesn't really play a huge role in these cells, does it? Right? There is a little bit there, but at least norepinephrine doesn't activate it to any great degree. Now, a nonalol, granted, again, if I could go back and redo this graph, I'd probably make this blue bar a little bit higher, just so you guys can, so it's not as confusing, but you got the right idea there, okay? All right, let's take a look at cyclic AMP levels. Same thing here, same graph, it's just a different second messenger, okay? So here we have cardiac muscle cells. All right, our basal level of cyclic AMP is about 3, maybe 2.5, 3. When we add norepinephrine, it shoots all the way up to about 7. And then when we add norepinephrine and ananolol, it returns back to basal. So do we think that ananolol has an effect on cyclic AMP production in cardiac muscle cells? So here's norepinephrine, right? We get a big, robust cyclic AMP signal, and then when we add norepinephrine again, the same amount, plus ananolol.
It doesn't have an effect directly on cardiac muscles.
What's that, Justin?
It doesn't look like it has an effect directly on cardiac muscles, but it does block the receptors.
Yeah, so for cyclic AMP, yeah, it is blocking the receptor that is coupled to the cyclic AMP pathway, right? So we can say that ananolol seems to have an effect on cyclic AMP production in cardiac muscle tissue. Okay, so again, we have basal levels here, right? That's unstimulated cardiac muscle cells. And then when we add a bunch of norepinephrine to it, look what happens to cyclic AMP levels. They shoot way up, right? So we know that cyclic AMP is produced in these cells when they're exposed to norepinephrine, and it's produced at a pretty high level. But then when we add ananolol to it and norepinephrine again, do we get the same kind of cyclic AMP signal?
No.
Nope. All right, so ananolol is blocking cyclic AMP production in these cardiac muscle cells, okay? All right, let's take a look at the SA nodal cells here, okay? We have basal levels of cyclic AMP. We add norepinephrine, and look, cyclic AMP levels shoot up pretty significantly. And then when we add norepinephrine and ananolol together, look what happens to cyclic AMP levels. They go back down to below basal, right? So is ananolol have an effect on the SA nodal cells? Yeah, absolutely. Absolutely it does, right? Very good. Very good. Okay. And then we go over to smooth muscle cells here. All right, so we have basal levels of IP3, or I'm sorry, cyclic AMP here. All right. When we add norepinephrine, we don't get anything, we don't get any kind of cyclic AMP response, right? Nothing. Okay. And when we add ananolol, we get about the same thing. All right, so I know there's some differences in the heights of these, but essentially there's really no response. Smooth muscle cells don't generate cyclic AMP in the presence of norepinephrine, and ananolol doesn't have any impact on that. Okay, so what are our two cell types here that seem to have be sensitive to ananolol?
The cardiac muscle cell.
Yeah, the SA nodal cells, right? Okay, good. All right, so let's go back up here real quick. Okay. So what types of signal transduction mechanisms seem to be affected by ananolol? So we looked at 3 of them, right? Change in membrane potential, cyclic AMP production, and IP3 production. So which one of these tends, and we're not talking about any particular cell type, but which one of these signaling mechanisms are impacted by ananolol? What do you guys think? Anybody? We got
The
three of them.
GPCR.
The GPCR ones, right, Daphne? Which ones are those?
Oh, the G coupled protein.
Right.
IP3.
Yeah, IP3 and cyclic AMP, right? Absolutely. So
Yes.
those are the two that are impacted. Very good. And what cell type seems to be the most sensitive to unknownalol?
It looks like the smooth muscle cells, right?
Yeah, so
SA
there's,
nodes.
go ahead. Smooth
SA
muscle cells?
nodes.
Go ahead, Priscilla.
I put SA nodes in the smooth muscle cells.
Yep. And what else?
I guess all three.
Yeah, Priscilla, I would agree with you. I think that, depending on what signaling pathway we're looking at, right, all three of these cells seem to be sensitive to unknownalol in some way or another, right? Okay. And so what specific types of receptors or receptor families that may be targeted by unknownalol? Well, we've already ruled out ligand-gated ion channels, and we can see that GPCRs, right, are probably our receptor type that we're looking at here. And I'm trying to remember who said adrenergic before. Iman, was that you? I can't remember, but you said somebody said adrenergic receptors is probably what's going on, is the type of GPCR that we're targeting here. And how do we know that? Yeah, because we're in cardiac and vascular smooth muscle tissue where adrenergic receptors activate these signaling pathways. Okay, so there's a little bit of extrapolation that you need to do, a little bit of thinking on this. Okay. Anybody have any questions about this as we move forward?
Dr. Culhane, I have a question
Sure,
about
Kayla.
the third one. So when you say it's dependent on the pathway, so the one that would have the effect for IP3 is the smooth muscle, and then cardiac and SA node for cyclic AMP?
Yep.
Okay.
Yeah, so exactly. So again, depending on what signaling pathway you're looking at, I think we can make an argument that all three of these cell types, albeit each one a little bit differently, is sensitive to unknownalol, right? Depending on what we're looking at. Okay, very good. Any other questions? All right, let's take a look at memorandum number 2. Let me stop sharing here. Okay. Memorandum number 3. Okay. All right, so the molecular pharmacology lab has finally been able to finish up the radioligand binding studies I asked for 2 weeks ago. Okay, I'm not a very good CEO. They found out that the unknownalol will bind to receptors in arterial vascular tissue and cardiac muscle. The pharmacokinetics group says that we get a plasma concentration of unknownalol, okay, of 3.47 times 10 to the minus 9th molar 45 minutes after a 10 milligram dose. Okay. So again, what we're saying here is that when we administer unknownalol to an organism, okay, that it takes some time for unknownalol to be digested and move into the bloodstream and get to the receptors. So it takes about 45 minutes for it to peak. And we get a peak dose of unknownalol after 45 minutes of 3.47 times 10 to the minus 9th molar, okay, after a 10 milligram dose. And our plasma concentration of unknownalol 45 minutes after a 100 milligram dose is 7.88 times 10 to the minus 6 molar, okay? Using the data below, can you tell me something about how selective our compound is at a dose of 10 milligrams and 100 milligrams, okay? So what we've got here, folks, with this is that we've got 2 different doses of unknownalol, 10 milligrams and 100 milligrams. And what we're doing is we're measuring peak plasma concentrations of our unknownalol 45 minutes after administration. It takes that long for unknownalol to reach peak concentrations in the blood. And that would essentially be the same concentration that would be in the receptor biophase, okay? So after 45 minutes, the concentration of ligand outside the receptor at 10 is either 3.47 times 10 to the minus 9th, or it is, let me see here, 7.88 times 10 to the minus 6. Okay, now let's take a look at our KD values. Okay, What we've determined is our KD value that ananolol has for alpha-1 receptors is 1.9 times 10 to the minus 9th molar. That's the KD value, the concentration of drug required to bind 1/2 of our receptors. And that's a reflection of how strong ananolol will interact with alpha-1 receptors, right? Okay, now, 1.9 times 10 to the minus 9th molar. Based upon that number, do you think that that's a good affinity or KD value? Does ananolol interact with alpha-1 receptors really well or not?
Maybe.
Okay, Roberto says maybe. I like, way to commit, Roberto. I like that, okay?
But
What do you
it can have effects in alpha.
Yeah, I think so. Roberto, I would agree with you. I do think that 1.9 times 10 to the minus 9, that's nanomolar concentrations, right? That's a
It's
good
a low,
KD.
it's a low KD.
Yeah, it's a very tiny KD, right? And the smaller the KD value, the stronger the affinity, right? All right. Let's take a look at KD for alpha 2. 2.31 times 10 to the minus 8th. Okay. Let me ask you that question. Does ananolol have a stronger affinity based upon those numbers for alpha-1 receptors or alpha-2 receptors?
Alpha-1.
Alpha-1.
Yeah, and how do you know that?
Because the KD for alpha-1 is smaller than the KD for
Exactly. Very good. All right, let's take a look at the KD for beta-1 receptors. 1.22 times 10 to the minus 12th. What's 10 to the minus 12th? What's the metric unit for that?
Pico.
Pica, don't forget that, okay? So what do we think about the affinity of ananolol for beta-1 receptors?
It's really strong.
It's really strong. It's the strongest, right? And then the KD for beta-2 receptors, 2.55 times 10 to the minus 7th molar. What do you think?
That's the largest KD for all of the receptors.
Yeah, so it's probably, it's got the poorest affinity, right, for beta-2 receptors out of all three of those. So if we were to rank order these, okay, make a list of these in the order of their affinity, starting from the strongest affinity to the weakest affinity, our first receptor with the strongest affinity for ananolol is our what?
Beta-1.
Beta-1, followed by?
Alpha-1.
Alpha-1, followed by?
Alpha-2.
Alpha-2, followed by?
Beta-2.
Excellent. Okay, so we can rank order those. Now, the big question is, which one of these receptors is ananolol going to interact with at these two concentrations that we have up here in our description? All right, so let's take a look at 3.47 times 10 to the minus 9th molar. Okay, so that's the concentration. Now remember, KD, the value of KD, all right, is the concentration of drug required to bind 1/2 of our receptors in our receptor population, right? So for example, if we add ananolol to tissue at a concentration of 1.9 times 10 to the minus 9th molar, 1/2 of those alpha-1 receptors will be bound up, right? That's the definition of KD. What if we add a concentration what if we add 3.47 times 10 to the minus 9th to our tissue type? What do you think about the alpha-1 receptors? Are we going to bind 1/2, more than 1/2, or less than 1/2?
Would you bind more than 1/2?
More than 1/2, and why?
Because that number is over the amount needed for the 50%.
Perfect, exactly, right? So that the concentration of ananolol we're talking about here is above the KD value, meaning that it will bind to more than 50% of the receptors, right? Okay, so at 3.47 times 10 to the minus 9th molar, will ananolol bind to alpha-1 receptors? What do you think? At 3.47 times 10 to the minus 9th, will ananolol bind to alpha receptors?
Yes.
Yes.
Absolutely it will. Okay. All right, let's take a look at alpha 2 receptors. Okay. So the KD value, the affinity value of unknownable for alpha 2 is 2.31 times 10 to the minus 8th, right? Okay, now let's compare that to the dose of unknownable that we're giving, which again is 3.47 times 10 to the minus 9th. Okay, so at this dose of unknownable, what percentage of alpha 2 receptors will be bound up? Will it be 50%, greater than 50%, or less than 50%?
Less than.
Greater?
Okay, so is 3.47 times 10 to the minus 9th equal to this? No, right? Is it greater than this? No. Is it less than?
Yes.
Yes. So we're going to bind to less than 50% of the receptors. All right. So as a general rule of thumb, when you're working through these problems, all right, and get your pencils out or get your fingers on the keyboard because this is important. The way to work through these really easily, okay, is you compare anytime. So you can, if you compare the KD value, all right, for the drug receptor interaction that you're talking about to the dose that you're applying, okay, if the dose is above the KD or greater than the KD, if the value is greater than the KD, then you're going to bind more than 50% of the receptors. And that drug will bind at that dose really well, all right, to unknownable or to the receptor, okay? If the dose of unknownable or any other ligand that you're giving your system is below the KD value, you're going to bind less than 50% of the receptors. And so it won't bind very well, okay? If the dose of your drug that you apply to your system is equal to the KD, then you know that 50% of the receptors are going to be bound up with the drug, which is pretty good, okay? So all we have to do is compare the dose that we're giving to the KD. If the dose of the drug that we're giving is above the KD or greater than the KD or larger than the KD, then it's going to bind really well. If it's smaller than the KD value, then not so much, okay? And if it's equal to the KD value, that means that at that dose of drug, 50% of the receptors will be bound up. Does that make sense to everybody? It's just about knowing what number is larger or smaller than the other. That's it, okay?
That makes sense, Dr. Hank. Can we get a little bit of clarification though? So for the KD for alpha 2, that number is larger than the dosage, right?
Yes.
So in this instance,
I'm sorry, you're right. Yeah, it will bind. It will at so in this instant, right? Okay, it will bind to alpha 2 receptors. Okay.
and what if that would be less than 50%, or would this be more?
It'll be more than 50%. Right.
Okay, but the concentration is small, but the concentration is smaller than the.
Oh, I'm sorry. Yeah. All right. So yeah, Justin.
Yeah, these negative nines and stuff.
Yeah. Give me a second here. Okay. Just 1 second here. I'm gonna recaffeinate. Okay. So let's take a look at alpha 2 receptors. Okay. So what's our KD value for alpha 2 receptors? It's 2.31 times 10 to the minus 8th. And don't even worry about these numbers here, 2.31. At this point, just look at 10 to the minus 8th, right? We know that our KD value is somewhere in the 10 to the minus 8 range, right? Now, the dose that we're giving is 10 to the minus 9th, right? So again, it's a tinier number. 10 to the minus 9th is less than 10 to the minus 8th, right? Okay. And so the dose of drug we're giving is less than the KD value by a factor of 10, right? If we're moving from minus 8 to minus 9. And so we can say that the ability of unknownable to bind to alpha 2 receptors at this dose here, it's fairly bad. It's not really good, okay? Because we're below the KD value. All right, does that make sense, Justin? I'm sorry if I screwed you up there.
No, that makes perfect sense.
Okay, good. Now let's move on to the beta 1 receptor. Okay. This one hopefully is fairly easy, right? What's our KD value? 10 to the minus 12th, right? The 1.22, which we don't really need to worry about right now. It's 10 to the minus 12th. So this is a really good affinity, right? Now, if we add unknownalol at a concentration of 3.47 times 10 to the minus 9th molar to our system, okay, is that number greater than 10 to the minus 12th, equal to 10 to the minus 12th, or less than 10 to the minus 12th?
Greater.
It's greater by a factor of 1,000, right? So what can we say about unknownalol and its ability to bind to beta-1 receptors at this low dose? Good, bad, or not so good?
Good.
Very good. It's very good, right? Okay. Now let's take a look at the KD for beta-2 receptors, okay? And unknownalol. Our KD for beta-2 receptors is 2.55 times 10 to the minus 7th molar, right? Okay. Is our dose here minus 9, is 10 to the minus 9 greater than the 10 to the minus 7, equal to 10 to the minus 7, or less than 10 to the minus 7? Yeah, it's less. It's smaller, right? By a factor of 100. So will unknownalol at this dose bind to beta-2 receptors very well?
No.
No. Okay, so now with all that being said, at this low dose, what receptors is unknownalol specific for?
Beta-1.
Beta-1, and what else?
And alpha
1.
1.
Yep. Okay, very good. All right, so again, at that dose, we can say that unknownalol will bind to alpha 1 and beta 1 receptors. Okay. Now, let's bump the dose up to 100 milligrams. We're going to get to a very large dose. Okay. And at 100 milligrams, the plasma concentration is 7.88 times 10 to the minus 6. 10 to the minus 6. All right. So we compare 10 to the minus 6 to 10 to the minus 9th. Is that greater than, equal to, or less than 10 to the minus 9th?
It's greater.
It's greater, right? So will unknownalol at 100 milligrams bind to alpha 1 receptors?
Yep.
Absolutely it will. Okay. How about for alpha 2 receptors? Is 10 to the minus 6 greater than 10 to the minus 8th, equal to, or smaller than 10 to the minus 8th?
It's still greater.
Yeah, so will unknownalol bind to alpha 2 receptors?
Yes.
Absolutely. At this dose, it will now. See, now we're starting to lose selectivity and specificity, right? Okay. What about beta 1 receptors? Will it bind to beta 1 receptors at this dose?
Yes.
Absolutely, it will. It bound very well at the lower dose, so why not at the higher dose, right? Okay, 10 to the minus 6th is much larger than 10 to the minus 12th. Okay. And then what about beta 2? Is 10 to the minus 6 greater than, equal to, or less than 10 to the minus 7th?
It's greater.
Yeah, so will it bind to beta 2 receptors? Yeah,
Yes.
absolutely. So you can see what's happened here, folks, right? Okay. Is that at a 10 milligram dose, unknownalol seems to only bind to alpha 1 and beta 1 receptors fairly well, right? But when we bump the dose up to 100 milligrams, right, now we get spillover in interaction with the other 2 receptors, the alpha 2 and the beta 2 receptors. Okay. Does that make sense to everybody? Okay. So again, this exercise is really, really important for you to do. Okay, I'm going to stop sharing here for a second so I can see folks. You may have to do something like this on an exam. So if you didn't understand that, or you're not really sure about it, go through it again, reach out and let me know if you need some help with it. And another way to do it is just to change some of those numbers around. Okay, if you're studying with somebody, change the numbers around, because I just made those numbers up. Okay, change the plasma concentration, change the KD values for the different receptors, and practice. Okay, and again, if you just remember that simple rule, if the dose of your drug that you're giving is above the KD value, okay, then it's most likely that that drug is going to interact with the receptor at that concentration or dose. If it's equal to the KD value, then you know that the drug is binding 50% of the receptors. And if it's less than the KD value, then you know that the drug is binding to less than 50% of the receptors. Okay? Does that make sense? And it's probably not binding very well. All right.
Can I ask you a question?
Sure, Eric, go ahead.
So as you increase the dose of any type of drug, I know for a fact you lose selectivity, but do you also lose specificity?
Yeah, you do. So you lose both selectivity and specificity, meaning that the drug is less selective, right? And the list of receptors that it will now interact with is longer. So it's less specific, right? Think about our example here. If I asked you what is the specificity of unknownable at 10 milligrams, what would you say? What are the two receptors it would interact with? You guys there? Hello? Uh-oh. Hold on one second. Okay, you guys there? We froze up for a second.
Yes.
Okay, sorry about that. Okay, Eric. So at 10 milligrams, what are the two receptors that unknown law will interact with?
Alpha 1 and beta 1.
Right, so that's your specificity, right? It's specific for alpha 1 and beta 1 at 10 milligrams. But at 100 milligrams, what's the specificity?
All of them.
Yeah, alpha 1, beta 1, alpha 2, and beta 2. Very good. Okay, so you can see we're losing specificity and we're losing selectivity.
Okay, awesome. Thank you.
You're welcome. And that's important to know too, okay?
Dr. Cohen,
yeah.
What's the format for like our quizzes and exams? Is it multiple choice or essay questions?
So there'll be a mixture. Okay, you're going to have, I think probably about 60% of the exam is multiple choice. And then the other 40% is a little bit of short answer. And you might have one or two questions like your self-assessment questions that just require a little bit of thought. Okay. All right, let's go to the notes. Let's get back to our discussion here. All right, so example, one of the things I asked you to do was to do example 1. Okay. All right, can you guys see the entire slide here? You guys can see the entire slide? Okay, good. So all of this example really just required you to do was to take the KD equation, L times R all over LR, and calculate a KD value based upon what I've given you up here. Okay. So I asked you to work on that. Let's take a look at the answer here. Okay. If you didn't notice, the answer was on the next page. And it's really just what I like to call plug and chug, right? Where you're just taking the values, plugging them into the equation, and then doing some basic arithmetic, right? Now, one of the things that I wanted to let you know here and to point out is that if you take a look at the numerator here, right, in your equation, okay, we're making adjustments, right? 100 nanomolar is the amount of ligand that you start off with before the reaction comes to equilibrium, okay? And 10 nanomolar is the amount of receptors that you have right at the beginning of the reaction before things start interacting with one another and before it comes to equilibrium, okay? So, and then once the reaction comes to equilibrium, this is the number of ligand receptor complexes that are formed, okay? So if we want to know how much ligand is left over after the reaction comes to equilibrium, we just take this number and subtract it from this number here. And if we want to know how many receptors are left over after the reaction comes to equilibrium, how many free receptors are left over, we'll take 5 nanomolar and subtract it from this. And this is what we get here. 95 nanomolar is our KD, okay? The KD for drug 2 Same thing here. Okay. And we get 81890. So the mathematics is pretty easy here. I think the spot where some students get a little bit tripped up on and confused about is making that adjustment to the ligand receptor concentrations, right? Because we know, okay, at equilibrium, the number of free receptors that we have is going to be less than what we started with, because some of them are going to be bound up with ligand, right? We also know that the number of free ligand molecules that are floating around in the biophase are going to be less than what we started with when the reaction hits equilibrium, because some of them are going to be bound to receptor. And that's why we have to make this adjustment. Any questions about this example?
Yeah, Dr. Cohen.
Yeah.
So when we did this, we did the calculation a little different.
Yeah.
Than what you did. So we used just we did 100 times 10.
Yep.
And then we just divide, for the first drug, we did 100 times 10, and then we divided it by 5. I mean, we still got the drug one to be less than, it was still less than the KD for drug 2.
Yeah, absolutely. And so, Masid, you know what, can you see the difference between what you did and what I did?
Yeah, because you did 100 minus 5. And then 10 minus 5 in the numerator.
Right. And do you understand why we did that?
No.
Okay. So let's go back. Okay. All right. Let me see if I can find. Yeah, let's take a look here. Okay. So let me give you just a really simple example here. Okay. So let's take a look at our law of mass action. L plus R yields LR, and we're gonna calculate a KD value here. Okay. Now, let's say in this reaction, in my tissue that I have, I've got 10 receptors. That's all I've got. 10 free receptors that are waiting to bind a ligand. Okay. 10 free receptors. And I add 100 ligand molecules to my receptor biophase. Okay, so those are the values that we're starting out with right at the beginning of the reaction. The reaction hasn't started yet. I got 10 receptors and I got 100 ligand molecules, right? That's what we're starting out with. Now, once I add the ligand molecules, the ligands are going to start to bind to the receptor, right? Until the receptor comes to an equilibrium. Okay, and let's say that when that reaction settles down and comes to an equilibrium, there are 5 ligand receptor complexes that are formed. Okay. How many receptors are left over that are free and unbound by ligand at this point?
5.
5, right? Okay. And how many ligand molecules are free and unbound to receptor?
95.
95, right? Now, let's take that and translate it to our equation. Down here, okay, this L and this R here does not mean the concentration of ligand and the concentration of receptor at the beginning of the reaction, okay? It's at equilibrium. So it is true, we started off with 100 ligand molecules and we started off with 10 receptors that are free and unbound by anything, right? But remember, we can only calculate the KD when the reaction's at equilibrium, right? So we have to make an adjustment. We can't just use the original values that we get for ligand and receptor. We've got to make the adjustment. Okay? So we've got to say, okay, we started off with 100 ligand molecules, but 5 get bound up after the reaction comes to equilibrium. So the number we plug in here, right down here, is going to be 95. Okay, we started off with 10, absolutely. But is there 10 free at equilibrium? 10 receptors free at equilibrium? No. How many are free at equilibrium? 5. So we plug in the number 5 here. See, does that help?
Yes, that helps. It makes sense then.
Good. All right, great. Because I will tell you, this is, if students get tripped up on anything when I teach this every year, it's that very thing. And there's always questions about that. So I want to make sure, I'm glad you asked the question to make sure everybody's good to go. You guys good to go on that? All right. All right, now what we're going to do here is, in the interest of time, okay, we are going to skip this slide here, this slide here, and this slide here, okay? And let's see, we're going to skip, yeah, we're going to skip this slide here and this slide here. All right. You will not be responsible for those on the exam, okay? Because we don't have as much time as I'd like, and because we missed some things from the fire drill the other day, and I have to leave class early. And this gets into a little bit more detail, depth, and complexity, and I don't think we need to go there this year. Okay, everybody good? All right. All right. So let's talk about efficacy. Okay. So there's a vocabulary to receptor theory, right? We talked about the term affinity, right? Which is got a couple of definitions, right? It's the strength of the interaction between the drug and receptor molecule, or ligand and receptor molecules, right? Yeah, it's also the concentration of drug required to bind 1/2 of the receptors in our population. That's our mathematical or experimental definition of it. And we know that affinity can also be described by the law of mass action, right? So if we were to take this equation right here, R plus L yields LR, yields a biological response, okay? This first part of the reaction right here, L plus R yields LR, is what describes affinity. So if I were to ask you on an exam to describe affinity using the law of mass action, all you would need to do is write L plus R yields LR, okay? Circle that and say that that is affinity, okay? That describes, that part of the law of mass action describes the strength of the interaction between the ligand and the receptor, okay? Now, efficacy. Efficacy is the ability of a ligand receptor complex to generate a biological response. So some ligands, when they bind to receptors, will activate them and generate a biological response. And you guys probably have already heard the term agonist. That's a ligand that will bind to the receptor and generate a biological response. Okay. So in this case here, if we take a look at our equation, and I just have the L's and the R's mixed up here, it doesn't matter which way it goes. L plus R yields LR, yields a biological response. And this little asterisk here just means that the receptor is now activated. That's, if you ever see an asterisk here, that usually means that the receptor is in its active form or active conformation, or it's been activated. Okay. So efficacy, the verbal definition is the ability of a ligand receptor complex to generate a biological response. Okay. And if we were going to use the law of mass action to describe efficacy, okay, all we would say is that it is the part of the reaction here where you have the ligand receptor complex that's formed and the biological response. So this right here, this part of the law of mass action, is efficacy. So if I were to ask you to use the law of mass action to describe efficacy on an exam, all you'd have to do is give me L plus R yields LR, yields biological response, and then circle the last part of the equation there, the one where I have the bracket on. That's efficacy, right? Because it's the ability of this ligand receptor complex to generate this biological response over here. Everybody got it? Good. All right. Now, an agonist. We already mentioned this. An agonist is any substance which binds to a receptor and generates a biological response. So if we're seeing the same equation here that we saw on the last slide, all we're doing is we're replacing the term ligand, which was L, with the letter A, which is our agonist. Okay. And here we have agonist plus receptor yields an agonist receptor complex. You see the asterisk there, right? Which means that this receptor is active and that will generate a biological response. That's the verbal definition of an agonist. And down below, this is the definition of an agonist using the law of mass action. So again, if I were to ask you on an exam, can you use the law of mass action to describe how an agonist works? It's real simple. It's A plus R, equilibrium sign AR, and then another arrow and biological response. That's it. Okay. And what you would probably, what's always helpful to do is define your terms. What is A? A is equal to agonist. What is R? R is equal to receptor. Okay. R star is equal to activated receptor. Okay. Everybody got that? We're good?
Can I ask you a question?
Sure. You can ask anything, Eric. Go ahead.
Is efficacy and agonist like synonyms, or am I missing something?
Nope. Efficacy is a term that we use to describe how powerful an agonist is.
Okay.
So agonists have efficacy because they generate a biological response.
Okay.
We have some very strong agonists that have a high degree of efficacy. We have weak agonists that have a low degree of efficacy. And then we have drugs that bind to receptors and don't do anything. And how much efficacy do they have? None. Exactly. Okay. So it's a term that's used to describe how powerful an agonist is.
Okay.
Okay. So yeah, definitely related. Does that help?
That helps. Thank you.
Excellent. What other questions do we have? All right. Now, let's talk about the different types of agonists. Okay, there's a bunch of different types of agonists. Okay. All right. So the first type we're going to talk about is a full agonist. Okay. So a full agonist, and these names for agonists are actually pretty good. They're pretty descriptive of what the agonist actually does. A full agonist is a substance that is capable of generating the maximum biological response a system can achieve at 100% receptor occupation or less. Okay. All right. So way back in the early days of the receptor theory development, we're talking about the beginning of the 20th century. Okay. And we'll talk more about this in a little bit. Early receptor theorists believed that in order for an agonist to generate a maximum response in a biological system, that they had to activate all of the receptors, 100% of them. It's sort of like if you get in your car and you want to achieve the maximum speed that your car can get, right? What do?
Floor it.
You floor it. That's right, Justin. You push that gas pedal all the way to the floor, right? Until it can't go any further. And that's going to give you a maximum biological response. Okay. Now, what later on, what was recognized was that certain agonists are so powerful that they can achieve the maximum biological response that a system is capable of by activating less than all of the receptors. Okay. So a full agonist is a drug that will generate the maximum biological response a system is capable of, either by activating all of the receptors that it can activate in the system, or some fraction or percentage less of those receptors. And I'll tell you the truth, there are some full agonists that are so powerful that they only need to activate 2, 3, 4, 5% of the receptors in a biological system, and they will generate the maximum biological response. Okay? That's like, yeah, go ahead, Justin.
How do you measure that? You just measure it by the desired effect? Like if you, for instance, like if it's hypertension medicine, if the blood pressure goes down, then it will be a full agonist? Or?
Yeah, yeah, exactly. So Justin, we measure this in the laboratory, and I'm actually going to give you some examples of this later on. But you have to, the first thing you have to do is in your biological system, when you're a scientist measuring this, you got to establish what the maximum response your system is capable of, right? So like, for example, the maximum response my 1995 Ford Escort was capable of was 85 miles an hour. That was it. Okay. So I knew no matter what I did, I wasn't going above that. Now, could I achieve the maximum response by pushing the gas pedal all the way to the floor? Yes. Okay. And so I knew that that's what it was. I wasn't going above that. All right. Now, if I was going down a big hill in my car, huge, long hill, I might only need to press the gas pedal down a little bit, right, in order to hit 85 miles an hour. I don't need the full capacity of the engine because I'm getting some speed rolling down the hill. All right, so that's kind of the analogy for a full agonist. Full agonist is a drug that will generate the maximum response that your system can generate, all right, and you have to be able to know what that is. And then it can do that either by activating all of the receptors or a fraction of receptors that are less than 100%. Okay. Full agonists have affinity and efficacy, meaning that they have the ability to bind to their receptor and they can generate a powerful biological response by activating that receptor through binding. So it's important to be able to use the terms affinity and efficacy to describe different types of agonists and antagonists. Okay. All right. Now, let me give you an analogy that I always use. Okay. And usually I act this out in front of the classroom, but because I'm on Zoom, I can't do it. But let's see if you can imagine this. Okay. Imagine we're in the Nod Auditorium. Okay. And I'm standing down in front, and there is a small car sitting right in the front of all the seats there in the front of Nod Auditorium. All right. I always say a Volkswagen Beetle. And some of you may know what that is and some of you may not, but it's a small car, right? Okay. And let's pretend that 6 of the Ravens offensive linemen are in the class with us. Okay. These are big, strong guys. They're like, hugely strong guys. Okay. And they're down in the front and they all get around the little car and they grab a piece of the car, the frame, and I ask them to lift the car up over their heads. Okay. And those guys are strong enough that they can actually lift the car all the way up above their heads. Okay. That's the maximum height that they can lift it is above their heads, right? These guys are an example of full agonists, right? Okay. Because there are only room for 6 of them around the car. Okay. And they're able to generate the maximum response that they're capable of doing, that the system is capable of doing. They're able to lift the car all the way up over their head. So they're full agonists. Okay. You guys got that? All right. Now, let's take a look at partial agonists, and I'll extend this analogy. This is a substance, okay, that produces, even at its highest concentration, okay, and 100% receptor occupation, less than the maximum response achievable by the system. So here we have an agonist that will activate the biological system we're talking about, okay, activate our receptors. But even when these agonists activate all of the available receptors in the biological system, the biological response that they get is less than the maximum response. So these agonists are weaker types of agonists. Okay, they're weaker than the full agonists. They still generate a biological response, but it's less than that of what you would get with a full agonist. Full agonists are really powerful and strong. Partial agonists are weak. Okay, and partial agonists also have affinity, meaning that they will bind to their receptor, and they have varying degrees of efficacy. Okay, some partial agonists are so weak that they have a very tiny amount of efficacy, where other partial agonists are pretty strong. and they have more efficacy, but they'll never have as much efficacy as a full agonist. They'll never be as powerful as a full agonist. Okay. So let me give you an example of this. Okay. Let me extend my analogy. So let's get back into the Knott Auditorium. There's a small car there in the Knott Auditorium, and the Ravens offensive linemen are there. Okay. Now, those guys are standing off to the side. They've done their job. They've been able to lift that car all the way above their heads, so they're full agonists. Now, we're going to bring in another team, okay, of people to try to lift the car. And these are our partial agonists, okay? So you're going to have myself, Dr. Shimoda, Dr. Dutta, Dr. Lin, Dr. Bailey, and let's say we'll pick on Dr. Haggerty today too, okay? So we've got 6 of us, right? All right, so we all get around the car, all 6 of us around the car, just like the lineman did, and we try to lift the car up, okay? Let's imagine that the 6 of us are strong enough to lift the car an inch off the ground, okay? What kind of agonists are we? We're partial agonists, right? We can still lift the car up a little bit, but not nearly as much as those full agonists could, right? All right. So that's what we're talking about here, okay? Now, let me ask you this question, okay? What if we mix the 2 groups? Okay? What if we mix the 2 groups? Let's take 3 Ravens offensive linemen and then 3 professors. Pick your 3 favorite professors, right? And we put them together and we ask that group of 6 to lift up the car. Do you think they're going to be able to lift up the car all the way over their heads?
Yes.
So 3 guys, do you think?
Probably not.
Probably not. Okay, I'm going to say that they're not going to be able to. Are they going to be able to lift it up higher than the 6 professors did? Oh, absolutely, right? We're going to do much better with the Ravens offensive linemen, right? Especially if you get rid of me, right? So we're going to be able to lift it up higher, but are those offensive linemen going to be able to lift it up over their heads with the 3 of us? No. Okay. So what are the 3 professors doing in this situation? They are blocking, right, the ability of the offensive linemen to lift the car up over their heads, right? They still contribute, but because they're not strong enough as the linemen, they can't help. The professors can't help to lift the car all the way above their heads, which is our full response, right? So in this case, if you have a situation where you are mixing full agonists and partial agonists in your biological system together, and they're activating the same receptors, the partial agonists can actually antagonize or prevent the full agonists from achieving the maximum biological response. Okay? So in this case, all 6 linemen, which are our full agonists, can lift the car all the way above their head. That's the full response, right? But if we substitute 3 of those with 3 professors, are the 3 professors going to prevent those linemen now from lifting the car up above their head? Absolutely, because we're just not strong enough to help them to do it, right? We can contribute a little bit, but not nearly as much as they can, the 3 additional linemen can, okay? So what I'm trying to tell you is when you mix the 2 in a biological system, the partial agonists, all right, will block, to some extent, the full agonists and prevent them from achieving a maximum biological response, okay?
Is this done purposely, clinically?
You know what? There's a couple of examples, Justin. Okay, like there's a couple of beta blockers that are partial agonists, Pindolol, Timolol. We'll point those out in the cardiovascular module. They used to be used for heart failure. They're not used so much anymore because they're just not very good, and they cause more trouble than they're worth. So that's the example of a partial agonist. Okay. So there is a clinical relevance to this, but it's just so that you understand why, how those drugs work. Okay. I will tell you truthfully, the vast majority of the drugs that you're going to talk about in pharmacotherapeutics are antagonists, are blockers. Very few of them are agonists. Some of them are, but there's a much greater number of antagonist drugs that we use therapeutically than there are agonist drugs. When we talk about agonists, I think it's really important, when we talk about neurotransmitters and hormones and other types of substances the body produces that will activate receptors, right? Those are agonists. But most of our drugs that we've developed are receptor blockers or protein blockers. Okay. Not all of them, but many of them are. All right. Inverse agonists. Okay. Inverse agonists. Okay. This is a type of agonist that actually produces a decrease in the basal activity of a system. Okay. So an inverse agonist produces a biological response, but it's the inverse of the biological response, or the reverse of it. So for example, let's imagine my 1995 Ford Escort. If I push down on the gas pedal and put it into drive, right, all the way to the floor, I can go 85 miles an hour forward, right? That's an example of an agonist. A full agonist or partial agonist, whatever you want to say. Now, if I put that car in reverse and I hit the gas pedal, I'm going to go in the opposite direction, right? That's sort of like an inverse agonist. Okay, we're going in the opposite direction. So one of the things that you need to know to understand inverse agonists, okay, is to understand that many of our receptors that we know about, that we've studied, okay, have spontaneous activity. These receptors can activate, okay, without any type of agonist present. All right, a lot of receptors can do this. They spontaneously convert between their active and their inactive forms. And so they generate this low-level basal level of activity. Okay? All right? And when we apply an inverse agonist, it lowers the basal activity of your biological system. Here's an analogy that I always use to describe this, and I think it's one that we can all relate to, I hope. Okay? I want to show, just give me a show of hands, how many people have ever played with a dimmer switch or a light dimmer switch? You know what that is? The dimmer switch? Right? So most light switches have, they go on and off, right? So you have your lights on or your lights off. But some light switches have, are dimmer switches, right? You can slide it up and down and the light gets brighter and it gets darker, right? Okay, everybody understand that, because if you don't understand that sort of thing, this analogy is not going to work. Okay, now, what receptor theorists used to believe, back in the early days, is that receptors were like old-fashioned light switches. They were either on or off. On or off, right? Now we believe that most receptors, okay, are more like a light switch that's a dimmer switch, right? So that your light is always on, but at a low level, all right? Sort of like mood lighting, right? You come home from a hard day, you turn your light on, and you pull the dimmer switch down so that you've got enough light to see around, right? But it's kind of relaxing. It's not glaring in your face, right? Okay? And so most receptor theorists these days believe that most of our receptors have this kind of basal level of activity, okay? Even when they're not being stimulated. The light's always on at that low level. When they interact with an agonist, the dimmer switch goes up and the light gets brighter, okay? If it's a full agonist, the light goes all the way up to its brightest setting. If it's a partial agonist, the light goes up a little bit, but not up to its fullest extent. And if it's an inverse agonist, the light will go from its low setting, its basal setting, down to darkness. So an inverse agonist will take a receptor's basal level of activity and turn it off. Just like we could take a light switch that's on a light that's on all the time that has a dimmer switch, but it's on at a low level when you're not there. Right? And an inverse agonist would be something that would take that light and dim it all the way down to the room's completely dark. Okay? Does that make sense? So let's take a look at this graph here. Okay? So here in this graph, we have on the y-axis here, we have percent receptor activation. This is the percent of receptors that are being activated. Okay? And here we have a line here that shows what our basal receptor activity is. This is like our light switch with a dimmer that is set really low. So imagine your light really, really low level here, right? But it's still on. Okay, it's not dark. There's a low level of light. Okay, our full agonist, when we stimulate these receptors with our full agonist, we get a big response here, right? We get 100% receptor activation. Our partial agonist, right? We get less than 100% of the biological response here, right? That's what a partial agonist is. And then our inverse agonist, when we apply it, can take the basal receptor activity all the way down to 0, meaning we take that light switch, that dimmer switch, which is on a little bit, we've got just enough light to see, and we turn it completely off. Okay, the partial agonist is when we take that dimmer switch, we turn it up a little bit, or maybe a little bit more, but not all the way up. And a full agonist would be when we take that dimmer switch and we push it all the way up, so the light's on its maximum luminosity. Okay, does that make sense? What questions do you have? Does anybody want me to explain that again? It's okay, because this is not an easy concept to visualize.
Yeah, because it's complicated because what's the difference between this and an antagonist exactly?
Ah, Justin, that's really good, right? And I will tell you, that's a great question. Justin's question is, what's the difference between this and an antagonist? Okay, and that we're going to explore that when we start talking about antagonists. And in fact, Justin, I will tell you that we do have some clinical examples of inverse agonists. Okay, do you see these here, Justin?
Yes, it's histamines.
Histamine blockers, right? So for a long, long time, we thought that histamine H1 blockers that we use for allergies, right, were classic antagonists. We thought they just blocked the receptor, okay? But when we began to look at them more closely, we began to recognize that they don't work like antagonists. They actually are inverse agonists, okay? So let me show you here. If I were to apply a classic antagonist to this system here in the slide, what do you think would happen to the basal receptor activity? Would it go up? Would it go down? Or would it stay the same?
It should stay the same, right?
It'll stay the same, exactly. So antagonists, and we're gonna go over this again on Wednesday in more detail, but antagonists don't change that basal level of activity that receptors have, their ability to spontaneously convert to their on or off states, okay? All antagonists do are to prevent an agonist molecule from binding the receptor. And we're going to get into that, like I said, in a lot more detail on Wednesday, okay? So it's a subtle difference, okay? And from a certain perspective, when you're at 60,000 feet, it's very difficult to see the difference between an inverse agonist and an antagonist. They look almost identical, okay? But if you get down to 500 feet and you're looking really closely at them, now you can tell the difference.
Okay. So
Does that make sense?
It has to be lower than the basal activity.
Exactly. An inverse agonist will lower the basal activity of the biological system, either down to 0 or something close to 0, depending on how strong it is and how much you give. An antagonist, when you apply it to the biological system, will not change that basal level of activity. So if we go back to our light switch analogy, if you were to apply an antagonist to our light switch, okay, or, all right, that's on at a very low level, it would sort of be like putting a steel box around that light switch. Imagine a steel box covering that light switch up. Can we get access to that light switch and change it now? No.
No, we won't.
No. So that's an antagonist. Will the light still stay on?
Yes.
Oh, absolutely, right? But it won't change, right? Because that antagonist or that steel box is around the light switch. If we remove the steel box or remove the antagonist, now can we move the slider switch up and down to change the light intensity?
Yes.
Absolutely, we can. Okay. All right. Any other questions before I have to go? All right, folks. So I will get those assignment things up. I'm going to be honest with you; it's probably not going to happen today. It's more like tomorrow because I've got a long day here. But just hold on to them. I'll make sure just make sure they're done. And once I get the assignment thing up, all you have to do is just upload them, and you're in good shape. Good work today. A lot of difficult concepts to talk about today, but it was some really great questions, and you guys participated really well. I'm very pleased. Okay. So if you're a little bit confused about this, go ahead back. I'll try to get that recording processed and posted today. Okay. And we'll go from there. Okay. All right, folks. That's it. We're done.
All right. Have a good day.
All right. You too.
Thank you.
Thank you, guys.
Thank you.
You're welcome. Hi, guys. Barbara, what's up?
Dr. Cohen, I
Yes.
just want to say that I have like problems with my internet connection.
Okay.
That's the reason that I entered like 3 minutes late.
Oh, that's okay,
So,
Barbara. I noticed you were in and out a little bit too.
Okay, perfect. Well, thank you so much.
You're more than welcome. Okay. Have a good day.
You too.
And thanks for letting me know. I appreciate it.
Okay. Bye.
Bye-bye.